So starting recording is about to. So yeah, so recording has started. I think we can get started. Okay. Okay. Hello and welcome everyone. So there are new people today. In yesterday's class, we discussed a bit about, some basics of probability and like what do we exactly mean by probability and how can probability work in mysterious ways. It was I don't know how was the lecture, but we discussed quite a bit about some non-trivial stuff about probability, which might look at first sight it might look like some sort of voodoo, but yeah, nonetheless it's yeah, quite interesting. Yeah, and we discussed some classical things like probability, total probability rule, conditional probability, what are independent events and stuff like Bayes rule and things like that. Okay, so this was like yesterday's lecture. If you have missed it, I will request you to please uh, uh, check out the YouTube link that I shared. The lecture is shared over there. Okay, so let us get started with today's portion. So the idea today is to at least go till MLE, maximum likelihood estimation, or at least complete the information theory part so that we can get started with MLE. But let's see. How it goes depending upon how much time we devote to questions and things like that. We will be able to see how it goes. Yeah. Okay. Okay, so uh, let us start with something new today, and that is what we call as random variables. Okay, so this is an important concept. Okay, like the thing is, people whenever like my guide you says this, right? He says that whenever in like ISA interviews or any academic interviews, where they ask, okay, what is a random variable? People answer stuff like, random variable is a variable that is random. Well, that is a very wrong answer actually. So, a variable is something that assigns that is already random. So, if I say like x is a random variable, okay, it is something which is just it is just a placeholder. That's it. How can a placeholder be random? It, it doesn't make sense. So let me give you a formal definition of a random variable. Okay, so let us think about it. Uh, okay, okay, let me just define some few things. Okay, so last class we saw about sample spaces, right? Sample space that we denote by omega, right? Then we define, okay, we didn't actually define probability, but let me define few stuff now. Okay, first is, okay, what is called as sigma field. Okay, sigma field, which I denote by F. Okay, so what is a sigma field, right? So sigma field, it is a collection. It is a collection of subsets of omega which satisfy certain properties. Okay, so uh, it is a collection of subsets. Okay, so subset, we know what is a subset, right? So let's say if your omega is like something like h and t. Okay, h, if I create this set H which contains only a single element, right? This is a subset of omega, right? We know what subsets are. So if I, again, tails is also a subset of, omega, because we can see it here. Well, now I say, okay, now something like phi, which is a null set, is also a subset of omega, because, you know, I can always, say that, okay, my sample space omega has ht and something called null null element, which is nothing. So it's like zero in some sense, that it is always there. And now what I do is I create a collection of these sets. So what I mean by collection of these sets, so let's say uh, script C is my collection, and it is a collection of subsets. So it has H as one of its element. This set subset is one element. T is another element. Phi is another element. Okay. So now C here, C is what we call as, it is a collection of subsets, because H is a sorry, H is a subset, we know that. T, this element itself is a subset of omega. Phi is also a subset of omega. And we have created a, collection. We have collected these subsets and, put together in one set, and we are calling that as C. So it is a collection of subset. Okay. But it also has certain properties. Okay. So what are those properties? Okay. Let us list them one by one. So first is, uh, um so okay, it is sigma field is it is okay, it contains omega as okay, rather we should write it like omega is contained in F. Okay, so you will know that omega is a subset of omega, right? This is a trivial statement, right? Omega is always a subset of omega. That is fine. So omega is there in this whatever set collection that I will make. F we should contain omega in it. Okay. The next property is that uh, F is closed under complements. Complements. So what I mean, so what does this mean? So this means that A belongs to F. Okay. This should imply that A complement also belongs to F. Okay. And third property is that F is closed under countable unions. What does this mean? So let's say if A1, A2, something like till AN, these are subsets of F. Okay. This implies that union of AIs, I equal to 1 to N, this should also belong to F. This is what it means. So if F is closed under any complement, this is what it basically means. So if it is closed under union, so closeness something closed under. So you see these words, right? Closed under union, closed under countable union, closed under complement. What it means that if I take this thing out, complement and countable union, okay, from this these sentences, and I apply these operations to any element of F, that element, the result of that operation should also belong to F. That is what it means. So I said A is so F is closed under complements. What does that mean? I take A, right? I take A, I apply the complement operation to it, and whatever I get should also belong to F. I said F is closed under countable unions. Okay, what does it mean? So I take a countable subsets of F. Okay, and then I apply a union over it. Okay, then that should also belong to F. That is all it means. Okay, so if any collection of subsets satisfies these three properties, we can call that as a sigma field F. Okay, and so you could ask, okay, why is sigma field even necessary? So the thing with sigma fields is that, um, we yesterday, I think we discussed something that is relevant here. So we so let's take two examples. Okay, like first example is that of coin tossing. Coin tossing. Okay, and let's take second example as breaking the stick at random. By the way, can you just confirm if I am audible or not, please?
Yes, yes, yes. We are super clear. Go on.
Okay. Okay, so let's take these two examples. Okay, so okay, let us think about it. Okay, now let us take the coin tossing example first, so that I can make my point. Okay. Yeah. So so you know that omega here is this thing. Omega here is what, h comma t, right? We have only two possible outcomes. Now, okay, so let's say someone asks me that, uh, okay, what is the, well, tell me the probability of, uh, let's say, so let's say I am tossing the coin for, let's say, what, 3 minutes, 3 times, okay? So if I toss the coin 3 times, so okay, so I mean, what I want to say is perhaps something like this, right? So probability of any event A is what? Uh, uh, it will be like cardinality of A upon cardinality of omega, right? That is what it is essentially. So for example, if my A, this event is getting getting ahead, let's say. So P of A is what? What is so how many elements of this so what is the cardinality that is that I would like? It is, so there is only one outcome that is of interest to me, that is when I get ahead, I take this cardinality, right? And I take cardinality of omega, which is what? Which is heads comma tails, right? And this is basically cardinality 1, this has cardinality 2. So the probability comes out to be half. Okay. Now similarly, if I, if I, let's say that I am tossing the coin twice. So, and I ask you what is the probability of getting two heads? The probability of, let's say, two heads. So I will say, okay, what are the, favorable outcomes for me? So, okay, I see that, okay, only one possible outcome, which is heads comma heads, is favorable for me. And the total number of possible outcomes is, head, head, comma, head, tail, tail, head, tail, tail. Yeah. And I take the cardinality of this becomes 1 by 4. So, I mean, this is the typical way of calculating any probability that you give to me. And, I can do some combinatorics, it's just a counting problem afterwards. But if I come here, breaking a stick at random. So, and I give you, okay, what is the probability of, breaking, breaking the stick, breaking the stick at middle point, okay, at 0.5. Remember, we had some stick is something like this. You have 0 here, you have 1 here, and here is 0.5. I'm asking, so you break the stick randomly at any point, and I'm asking you, okay, what is the probability, that this thing it breaks exactly at 0.5. Now you say that, okay, what I will do is, I will just, do apply these kinds of formulas what we had here. I will use this type of formula. And I said, okay, go ahead. So you say that, okay, what is my favorable set? What is my favorable set? Cardinality of, so there is only one point that is of interest to me, that is 0.5. Okay. Now what I do is, okay, so fine, 0.5 is what now. Okay, but now I have to, I have to put this something like this here. And so remember, right? So okay, I hope you agree that this cardinality will be just one, right? Now I have to define the cardinality of this thing. I hope you remember that the omega for yeah. Well, now you will get, confused that, okay, what does it even mean to, have a cardinality of such a set? Does it even make sense? Because this is like, I don't know how to. Are you getting my point? I mean, there are infinite number of points here, right? Like, I hope you will agree that there are infinite number of real numbers in between here, 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 here. Like, you cannot count them. Would you agree with me here? Is this clear? Why
Yeah,
we cannot calculate the cardinality of this set?
yeah, because there's no discrete amount of like
Yeah.
state space.
Yeah, exactly. So that's why we cannot, calculate this thing. And I mean, eventually, we are in a trouble now, right? I mean, there is no way I can, formally, but this should make me, angry in some sense, because it's a simple thing. Someone is asking me to calculate a probability, and I'm not able to do it. For such a simple example of just breaking a stick at random, and in real life, there are even we come up with even harder test cases, like, you know like there can be even more complicated stuff that we can come up with, right? So uh, so these kinds of problems arise when we deal with what we discussed yesterday, uncountably uncountable. So there was something that we had discussed here. We discussed that sample spaces could be of three types. So, and particularly the worrisome cases are those of countably finite and countably infinite cases, when we cannot actually count the elements of your set, right? Sorry, I said it wrong. So countably infinite and uncountably infinite sets, sample spaces, because there are infinite elements or we cannot count them. So in such cases, we are in trouble. So basically, in those cases, the idea is that, okay, uh, well, I cannot, calculate cardinality, so to say, of this entire set. The main issue, what is the main issue with this? What is the main issue with, this set? Let us write those things down. So the first issue is that, uh, cardinality in itself is an issue because it requires us to count, you know and since this is not countable, I mean, it is an uncountable set, how can I count, and how can I even, come up with this thing? And second thing is that, uh, R01 is a large set. It's a very large set, it has so many elements in it, and we cannot handle, and we are not able to handle such a large set. Such a large set. So, like, these are the two broad issues that are there with this thing. If we can somehow, circumvent these things, then maybe we can, think of coming up with some notion of probability. So, okay. So I have now we know the what the problems are. Okay. So this problem is solved. Uh, this problem is solved by something called probability measure. Okay, and this problem is solved by sigma field. Okay, so what do I mean? Okay, the okay, so idea. So we will see what we will see what this, what do I mean by this thing. Okay, but let us focus on this first. Let us first focus on this thing. So what? So here is the idea, right? Sigma. So in some sense, we give up the idea of assigning a measure to this entire. We give up the idea of assigning a measure to this entire large set R0. We say that okay, it's a very big set. It is not possible for me to handle this such a big set, such a large set. So what I will do is I don't want to deal with this set. Instead, what I will do is I will come up with another set which has elements that I am interested in. So what do I mean by that? So let's say that so let me just write these things. Okay, sigma field, just give up the idea of assigning a measure to whole omega, whole sample space omega. Instead, assign measure to a smaller collection which contains the elements of my interest. So, for example, let me tell you let me give you an example. So, I said that okay, R01 is a very big set, and I cannot assign. It's difficult for me to deal with this set. So, what I do is okay, I say that oh, all right. So, what is of interest? What is it that is of interest to me? What is it that is of interest to me? Oh, I said that okay, well, let's say, I mean, here is your real line. Here is 0. Here is 1. Let me think of it. Okay, I want maybe the thing that is of interest to me is just intervals. Okay, like I am only concerned about what quantities that are intervals, and I can manage with it. So for example, suppose someone is asking me about things like okay, this is 0 point, let's say 4, and this is 0.6. What is the probability that you break a stick in this range between 0 point and 0 0.4 and 0.6? So I mean, if I have to so for example, I just want to deal with these kinds of sets, which I mean, how do I explain it? I just want to deal with a collection of sets which contains these types of subsets. So like 0.4 to sorry 0.4 to 0.6 kind of things, or maybe I want a collection of subsets which has elements like 0.4 to 0.5, and let's say union 0.5 comma 0.6 comma 0.8, things like that, weird things like this intervals and all. So am I making sense here, or is it I'm not able to explain it?
No, no, yes, yes. So, like, can you explain that, like, if we are defining these intervals, right? Like,
Yeah,
how will we be able to assign them weightages? Like, if I'm
right,
defining
right, right. Yeah, I'm
yeah,
coming to that. Yes, right. So but the idea of sigma field, I mean, is the motivation clear, that why do we need a sigma field, is that part clear?
yeah. So, so what I have understood is that sigma fill is required for like so if I want to, so I have some XYZ event, I have some event to be performed, right? And then event is not like for the stick to exactly find that how what is the probability of the stick being broken at 0.5, right? That is not
Yeah.
measurable. So what I do is I get a range in which that event falls, that the subsets of that event being performed, something like that, right?
Yeah, so so the idea is, yeah, I mean, you most of the part that you said was correct. So I mean, in some sense, yeah, you are correct. The idea is to, come up with a notion of, I need to come up with I want to see, I should come up with something which I know is of interest to me. For example, these intervals are good. You could have taken, I don't want to make so interval is, so you could have said that, okay, interval is of no use to me. I want my points to be there, I just want, I want my elements. I want a collection of subsets that contains like something like this thing, just points, 0.1, for example, or I mean things like that. So it turns out that interval is a kind of thing which allows you to come use any of these. I mean, intervals are basically very powerful. That's all. Let me just tell you that using intervals you can create any kind of element that you want. So it could be a point like 0.1. It can be a like disjoint union of sets like this one, or anything that you want can be constructed using intervals, open sets, so to say. Okay. uh, Maybe it is actually difficult to explain it all in such a short time because it's a deep concept, I agree, but nonetheless it is something which is very important, and it is at core of probability theory. Well,
Yeah,
okay, so
yeah.
let me just end this by just saying that intervals is all you need. Okay, using intervals you can construct open sets, you can construct points, single element things, or you can construct various weird things. How you can construct it, maybe you can look up on internet or google it and you can find out how is it very important. Okay, okay, so you will say that, okay, you gave us so much gyan. Okay, I told you, okay, this is why sigma field is required because R01 is such a large set. It is not possible to, deal with it. So I will come up with a collection of subsets. Well, now you will ask me, okay, so what is the collection of subset that I propose? So, okay, so the idea is that, sigma field. So this is how it is written. So sigma field of open sets, just let's call it open sets, is of interest to me. So what are open sets? So open sets are like which has elements such as uh, 0 comma 1 is an open set. Yeah, 0 comma 1 closed is also an open set. So anything 0 comma, it need not be 0, it can be 1 comma 2 union, let's say 5 comma 6 closed, things like this. Any open interval that you see at any end is good enough for me. Yeah, so if I create a sigma field using these sets, these open sets, that means uh, that means I ensure that all these properties are satisfied, that omega is contained in f, f is closed under complements, and f is closed under countable unions, and all those things. Then that subset, that sigma field, let me place this. So that sigma field is what we refer to as Borel sigma algebra. Okay, And this, it is of great importance for us. Okay, I mean, Borel sigma algebra is something that, you know, if you go in measure theoretic probability, it keeps popping on, and it is denoted by something called P of R. So B is for Borel and R is for, you know, because we are using open sets of real line, it is denoted as Borel sigma algebra. Okay, now this is all there is to, I mean, I think this is enough to, you know, describe what a sigma field is. Now coming to, you know, the second part of it, that is, you know, this probability measure. What is a probability measure? Hmm, probability measure. Probability measure is basically, you know, it is a function, a function that maps. Okay, it is okay. Probability measure is P of any set A that will where P of A is a function that maps that I don't even need A. P is a function that goes from the sigma field F to, you know, R. So this is a probability measure, or and this function. So it is a set function. Okay. So I will explain it to you, and let me just come to write one more thing. And this is the definition of any measure, a general measure, but probability measure is a special one, which assigns omega the a weight of 1. So, you know, in some sense, this is what probability is. Whenever we talk about probability, we are actually talking about probability measure. It assigns some weight, it assigns some weight to, you know, elements of the sigma field, and it assigns a weight of 1 to the sample space itself. And okay, so there is another property here that I should write. P of A should be greater than or equal to probability of B if A is a subset of B. So let me give you an example. Okay, so let's say that your omega is that of heads comma tails. Okay, and you know, you wanted to construct a sigma field about it, and you said that okay, let me take one. So my event of interest, let's say A, is that of heads. Okay, and someone comes and tells me, okay, this is my event that is of interest to me, which is the heads coming of heads. Now give me the sigma field that you said you will give me. Okay, so I said, okay, so you have A as your element. Now I look at the definition of, you know, sigma field. So omega is contained in F. Okay, so I say that okay, H is there. So okay, that is fine. But let me first come up. Let me see what. Let me put omega there. So H comma T should be also be there. Okay. Now again I go back and I see that okay, F is closed under complement. So if A is there in F, A complement should also be there in F. So okay, so I say that okay, what is the complement of heads? It is tails, right? So okay, so okay, tails is also there. Now I see that okay, heads. So this element, the omega element is there. So what is the complement of omega? So it is nothing but it is phi, right? This it is the null set. And now I check that okay, the third property that was there, okay, F is closed under countable unions. So I say okay, now I need to see if all the countable unions are there or not. So if H and T are there, union of H comma T is just the sample space, right? Which is this, it is already there. Now I see that okay, okay, let us take another thing. H and phi are there. Okay, so R is the union of H and phi here. Union of H and phi is nothing but H, so it is already there. So there's no issue. Again, similarly, tails is there. Tails and phi, the union of these two will be tails. Similarly, if I take head, this omega and tails as the two elements, and you know I take the union of these two, it comes out to be heads and I mean the omega itself. So So basically, this is all that is there in the sigma field of if your event of interest is heads, then this is the sigma field that is required, and that's all I need. Okay. Now you tell me, okay, now okay, fine. Was this clear? How I constructed the sigma field? Is this part clear?
Yes, yes.
So it was a simple thing, right? Especially in the case of discrete sets like this one, it is quite easy to come up with the sigma field. It is not a big deal. You can construct it very easily. All right. Now you say that, okay, now tell me the probability measure that you were talking about. So this is the probability measure. I see, okay, it is a function that assigns some real some real valued number to the elements of this sigma field f. And it should have a, I know that the probability measure for omega should be 1. So this element here should have a probability of 1. Now let's say I know that on the probability that the coin is being tossed. So the coin it is a fair coin, let's say, and I know that it has a half chance of coming up of heads, half chance of coming up with tails and things like that. So well, I said that, okay, fine. Then uh, uh, let me come up with this probability measure here. So I said that, okay, probability measure for head, let me assign that as half. Okay, this is something that I will decide. Probability measure is something that is governed by the environment, or the physics. So since I knew that heads has a it is a fair coin, I can assign it a probability of half. Now, what is the probability? So as I discussed earlier, the omega has probability of 1. So probability of h comma t has to be 1. Now, I think I missed something here. So probability of union of countable union of AIs should, if AIs are disjoint, then this is nothing but probability of AI. This is also one property that I missed. Okay. So, if remember what are disjoint sets, the if I take A1 and A2, AI and AJ in general, and I take the intersection of them, it will give me a null set because nothing is common between them. So this is these are disjoint sets, and if I use if I see what is the probability of union of such disjoint sets, it is nothing but sum of their individual probabilities. So using this, we can calculate what is the probability of tails. Right? Someone asks me, okay, what is the probability of tails? Okay, uh, I will say that, okay, what probability of you know h comma t is nothing but probability of h plus probability of tails. Someone would say, okay, why? Well, because H and T in themselves are disjoint sets, yeah. And I know that union of these two is this thing. So I mean, this will automatically hold. There won't be an issue, yeah. And one of them I know is half, and I have to calculate the probability of another one, and I know this is one. So probability of tails would be just 1 minus 1 by 2, which is 1 by 2. It's a simple thing. Actually, it is a trivial thing, but nonetheless, just to give you a simple example, that this sigma field and probability measure, these big terms are nothing new. It is something that we already know, but it's just that it will help us in some cases like breaking a stick at random where we were in trouble. Okay, so this was an easy example. Let me come to the breaking of stick example, yeah. Okay, so should I copy something here? Yeah, let me focus something. So, are you guys with me, or I don't know?
Yeah, yeah,
Is it
yeah,
fine?
yeah, yeah.
Okay. Okay. So this was the example that we were discussing, and we know that this thing, this approach, it got us into trouble basically. So let's not let's rectify this thing. So okay, now someone comes to me. Okay, you gave us this theory of using probability measures and sigma field and God knows what, and you promised me that you will rectify this issue that I was facing. So, and now you come to me and say that, okay, now rectify it. You gave us this theory, okay, fine, now rectify this thing. So, well, now I have to solve your problem. So let's see what is given to us, okay? So we know, okay, so we know that omega in this case is what? R01, yeah? This we already know. Now I have to come up with a sigma field. Now, so for now, just take my word for it. Borel sigma algebra that we defined here. The sigma algebra generated by these open sets. I mean, if we work with this, we will be fine. In most of the cases, Borel sigma algebra is all you need. Till date, I have not been able to find, an application in my research where Borel sigma algebra doesn't work. So Borel sigma algebra is something that will be fine. Okay. So what is a Borel sigma algebra? Sigma algebra, it is a sigma algebra that contains, these open sets that we discussed. Okay. So, okay. I mean, just to give you some, peek into what this Borel sigma algebra might look like. So let me just give you. It's not a complete thing. I cannot list all the elements of Borel sigma algebra, but let me list a few elements. Like to just to give you an example. Okay, what is this mysterious thing? So let me take one thing. Okay, so I know that it is, since it is a set of it is a sigma field generated by open sets. It must contain 0 comma 1 because it is an open set. Okay. Now I will go back and I will see that it must also contain its complement, right? So we know that it is also closed under the complement operation. So I will see that, okay, what is the complement of 0 comma 1? So, well, I know what is the complement of it is minus infinity to 0 closed union 1 to infinity. Is this correct? Because you have this number line which starts from minus infinity to infinity, and you have 0 here, you have 1 here, and the set that is given to me is this one. This one here. The complement of it is everything that is outside of it. Right? So what is outside of it? Outside of it is this entire thing and this entire thing. So I can take that, right? I mean, that is what I have written here. That is why this would also belong to this thing. Paste it here. Okay. So now, yeah. Now, since it is an open set, I also know that 0 comma 2 is also here. Because it is also an open set. So by this logic, it means that minus infinity to 0 union 2 to infinity is also here. Well, now we know that sigma algebra is closed under countable union. What a fool. Okay, paste it. Right. So I know that sigma algebra is closed under countable union. So that means if I take these two elements, right? Which elements? These, this element and this element. Union of these two elements should also be there in this Borel sigma algebra, right? So what is the union of these two elements? Let's see. So can I reuse this thing? I think I can. Okay. So here was your 2. Okay. Sorry. Yeah. So this thing is marked here in yellow, 0 comma 1 here is marked in yellow, this region, and minus infinity to 0 is this area, this region, okay, and 2 to infinity is something which is here. So what will be the union of these elements? It will be what? Minus infinity to 0. We know it is there. Okay. So let me write it. Minus in union 0 to 1. Yeah. Union 2 to infinity. So I hope you will agree that it will be minus infinity to. So this closed 0 and this 0 will merge, because this will continue. This will merge and this will be basically minus infinity to 1, 2 to infinity is what it will become. So this is also there in Borel sigma algebra. And similarly, you can see there are infinite number of elements here as well, right? I mean, I cannot list how many elements there are, because there are so many elements here. Have I made my point? Have I given you, how you can, deal with intervals and, construct sigma algebras, things like that? Have I given you some intuition into it, what it looks like?
Yeah, but like I still do not get the idea that how will I be able to find that the
Yeah,
probability
yeah.
of.
We are coming to the probability
Okay, okay,
part, but is this?
okay, okay.
Yeah,
Yeah,
yeah.
yeah. This is good enough for me.
Okay. So uh, yeah, let me keep it here. Yeah. Now coming to the major part, right? We will actually be dealing with the problem that we had earlier, right? That we were not able to count this thing here, and we were in trouble. So it's up to me what I decide. Okay, it's up to me what probability I want to measure. So what I will say is that, okay, well, my probability measure will be nothing but the length of the interval. Length of the interval. So it's up to me, it's up to me. So I decided, okay, p is nothing, my probability measure will be nothing but the length of the interval. Well, does this solve our problem? Let's have a look at what the problem. So this was what we had. So I now let you what this is. So probability. So right. So there is length of what 0.5, right? 0.5 omega, right? Here, what will it be? Anything? Okay, no response. So let me disclose it then. It will be nothing but 0. Okay. You can ask why. Well, because length of a single point is always 0. You cannot. So there is a single point here. So it has no length basically. That is what I'm trying to say. Uh, do you agree, or is it not agreeable?
But
What is it?
like the probability should be something, right? Because there will be a point where
It's not
we will be.
probability. That is the thing, right? It's not probability. It's a probability measure. It's a measure that we are assigning, right?
Okay.
It is a measure that we are assigning, and that measure turns out to be 0 for this element here.
So the way we measure it is by length of the set,
Yeah.
right? So,
Right. Yeah.
but like
Mhm.
when we measure a set where which says 0 to 1, we
Yeah.
measure
Yeah.
it as 1. Is that right?
Yeah. Yeah. Correct. So
Okay,
let
because
me give you some example.
I mean, I
Go
never
on.
studied like in anywhere that you can measure
Mhm.
like a set or a range in some sense. Because
Y- You can actually. So let me give you an example. Okay, so let me give you another example. What is the probability of breaking the stick, the stick in range, let's say 0.4 to 0.9, let's. So since I'm breaking a stick at random, someone asks me, okay, what is the probability that I will break it in the range 0.4 and 0.9. So in that case, this will be just, so it's 0.4 to 0.9, the length of this set upon length of, you know, what 0 to 1 is what it is. This turns out to be 0.
okay. So what intuition I'm getting from this is that since you cannot define a single point, calculating probability based on a single point doesn't make real sense. So we will need a range to calculate any kind of probability. Correct? Hello, am I audible?
Yes, you are audible, Ravi. Maybe Piyush, your voice is lagging. Hello.
Hello.
Yeah, Piyush, your voice was lagging in between.
Okay. So is it audible now?
Yeah, yeah.
Yeah, yeah.
You had a question?
Yeah. So what I was saying was that, in our undergraduate days, if someone had asked me this question, right, what I would have done is 0.9 minus 0.4 upon 1, which is 0.5. And I would have given him this answer, exactly this answer, right? I hope you will agree with me that, okay, this is what I would have done. But I
Yes.
mean, and this is the same probability that you are getting here. I mean, there's no change. It is just a formal notion. Okay, why should you do this thing? Why should you subtract 0.9, 0.4 to calculate the probability? It is a measure that you are assigning to that interval, and that measure turns out to be 0.5, and that way that is how you get your probability. uh, you were having some question. Please, if this is the part where I think you should have a lot of questions, and perhaps you should ask
Yeah,
as
so
many
like,
of them as you can.
So I was
so,
trying
Yeah.
to get an like intuition. Intuition I'm getting from this is that since you cannot define a single point because a single point like cannot be given a value, so you need to have a range to calculate such probabilities. So I think in any case of continuous measurement of probability, we need a range to calculate a case. Is that correct? So we can't like
Yeah, you are getting the correct intuition, I would say. You are like, your intuition is correct, that yeah, that in some sense that is what we are trying to do, that but I mean, it is not the point that we are having issues with. For example, here, we had a 0.5 here, right? We made a set, and the cardinality of that set was like 1. Okay, the problem that we were facing was actually this thing, right? I was not able to calculate the what is the cardinality of my omega. I mean, that is the point where I had issue, because it was not countable. I was I was not able to do this. Our our older definition, and try to calculate what would be the probability of this thing. So that would have been probably cardinality of 0.4 to 0.9. Okay, cardinality of this upon cardinality of 0 to 1. Now, this is infinity, because there are infinite number of real numbers between this, and this is infinity. And this does not make sense again. Whereas here, in this framework, it is much better and much more you know it is elegant, and you know do stuffs do stuffs with it and things like that. So it is the denominator that was giving me an issue. It was not, I mean, yeah, numerator also in this case is giving me an issue because it is infinity, and you know that probability cannot be, you know, more greater than one and things like that. So I hope dealing with in continuous valued things are a bit tricky here.
Okay, so
And
I get.
let me, yeah,
So
yeah,
what
yeah,
if
go on.
we have a case when we are calculating for multiple points, like when let's say that breaking a
Yeah.
stake at 0.5, at 0.2, and at 0.3. So I have three discrete values. How will we measure it then? Will it still be zero?
Yeah, yeah. So let us see what will happen, right? What is the breaking the stake at? What points did you set? Can you repeat?
0.5 and 0.2 and 0.3, like specific, not range, like specific points.
Yeah, correct. So this is this correct? Have I written it correctly?
Yeah. Hmm.
Okay, so fine. So let us see. You know, length of what this thing 0.5, 0.1, 0.13. Okay, and now length of 0, comma 1. Now denominator is 1, so let's not worry about that. So now what would be the numerator here, right? This is the question. Now to find this numerator, let me resort to this definition of, you know, probability measure. I had this property here, if you remember, right? The probability of union of AIs is summation of probability of individual if they are disjoint. Correct?
Hmm.
Is this correct? Yeah. So what would
Yes.
this be? L of, since you know 0.5, 0.1, and 0.13 are, they are disjoint, right? So
Yes.
this will become 0.5 plus L of 0.1 plus L of 0.13. Uh, Something like this. And you know all of them are 0, 0 plus 0 plus 0. This will also be 0, and hence this is also 0.
Okay.
So like,
So,
uh,
Yes.
yeah, so like, if we increase the, so by this, I'm like, if we increase the range of the intervals, right? So like if I am increasing from point 3 to point 6, right? So
Yeah, yeah.
I am increasing the range, right? So I am getting a number of point 3, right? And if I am
Okay.
taking a range of point 4 to point 6, I'm getting a probability measure of point 2 and point 3, right?
Yeah.
So what will these numbers signify? So like, what will it signify?
Mhm.
So the
So
question is,
it,
what is this? Yeah,
yeah, yeah. So, I mean, the answer to your question is, you know, mathematically, it just signifies the length of that interval, nothing else. Okay.
right,
I mean,
right.
I mean, ask yourself, right? What does it
Yeah,
signify? What does it
yeah,
signify?
but
It
yeah, but
signifies nothing but the length of that set. Yeah.
okay, yeah. So once I put it into the ratio, into the
Yeah.
formula, that cardinality of
Mm-hmm.
the length of
Mm-hmm.
the interval upon the
Yeah, yeah.
length of the. So what does this
Mm-hmm.
ratio now signify? So
Well,
what
this
does this
ratio, you
ratio say?
know, this ratio, what it signifies is what we call probability, basically. You know, what we understand from probability is this ratio, you know, that, okay, what is the measure, I mean, relative to, you know, the entire sample space, how much measure is assigned to the set that is of my interest, is what it signifies. That's all.
Right. So like if I want
So,
to go to point
so,
five, like
uh-huh.
yeah. So like if I want the point five, right? So
Mm-hmm.
the so like if I am decreasing
Mm-hmm.
I'm decreasing the length of my interval, right? So
Yeah.
I'll be getting the probability of
Lit-
me reaching that point will be less, right?
Yeah, yeah.
But logically shouldn't it be more, because as we narrow down the interval,
Mm-hmm.
0.5 would be more approachable.
So is your question something like, if the probability of, breaking a stick at point 0.5 is 0, right?
Yeah, yeah.
Then does
To
that
increase the
mean that,
probability, yeah, yeah.
does that mean that if I break a stick, it will never break at 0.5? Is that what you are asking?
No,
I
what
mean, are you
I am
trying to make
asking
sense
is,
of that?
yeah,
Yeah.
yeah. So what I'm trying to say is that as
Mhm.
the length of my interval increases, right?
Increases, yeah.
Yeah. So the probability of me reaching the point 0.5 increases.
0.1, this is 0.5. Yeah. You are saying
Yeah.
that, what do you mean by reaching a point?
Yeah. So like I want to see the probability of the event where I break the stick at 0.5, right?
Okay. Yeah.
So I take the probability measure approach, and what I'm trying to
Yeah,
do
yeah.
is I am trying to take the interval in
Yeah,
which
yeah.
point 5 lies, right?
Yeah,
So
okay.
I am taking 0.4 to 0.9. Okay. So
Right.
that interval has a length of 0.5. And
Yeah.
when I put it into the formula of
Uh-huh.
probability measure, okay,
Yeah, yeah.
that is 0.5
Uh-huh.
divided by the total length, that is 1. I'll get to the
Yeah.
probability of 0.5. Okay. So here the probability
Right,
of me
right.
reaching the 0.5, reaching the point 0.5 is 50%, right?
Right.
And if I decrease my interval from
Mm-hmm.
zero point 0.4 to zero point 0.6, I get
Yeah.
20%. I get 20%
Yeah.
probability of reaching that point, right? But
Correct. Yeah.
logically, the probability of me
Mm.
reaching that point 0.5 shouldn't
Yeah.
be more when I am in the interval between zero point 0.4 to zero point 0.6.
Okay, right. So I understood your question. So basically, you are saying that, okay, well, so if I understood your question is this. So if I break the stick in this range, right,
Yes.
the probability comes out to be 50%. Okay, with 50%
Yeah.
chance, I'm going to, break between this range. Okay.
Yeah.
But you're saying that, okay, now if I change this thing and my interval, and I want to get the probability of, breaking the stick between 0.4 and 0.6, it comes out to be 20%,
Yeah.
right?
But here the probability
And
should
then your
increase
question
because I
is,
am, yeah. Yeah.
yeah, but notice that what is your event? Let's see. The first thing was, probability of 0.4 to 0.9.
Yeah.
And the second thing was probability of 0.5 and, sorry,
4 and
0.4
6.
and 0.6. Yeah.
Yes.
This was 0.5, this was 0.2.
Yeah.
No, but well, in none of these cases, you specified that, I want to break the stick at point 0.5. Can you see that? I
Yes.
mean, the probab in none of these cases did you mention that, the probability, I want the, so I mean, so how do I explain this? So this is true for any point in the range 0.4 and 0.9. Does that make sense?
No, actually, it does not make sense to me.
So, so let's say I take this point 0.8 here, okay?
Okay.
So notice that we are talking about a range, okay? It is not specifying anything about the point 0.5, okay?
Okay. So,
I
like
mean,
you are saying that any point that lies between 0.4 to 0.9 will have the same weightage.
no, no, no. I'm not saying that. It's not about weightage, it is about the set that we are considering. It is like, if I, so what this is telling us is that, if I break a stick at random, the probability that it breaks between 0.4 and 0.9 is 0.5. That is all it is saying.
Okay.
It is not saying that,
Okay. Okay.
the probability of
Okay.
breaking a point at, let's say, 0.5 is, 50%
Okay.
or something like that.
Okay. Yeah. Now I get it. Now the probability of okay. In range.
Yeah,
Okay.
we are talking about range here. Yeah, and what you are trying to come up with is a single point, and that has a
Okay.
measure
So I
0.
was yeah. So I was like I thought that it will all lead to that what will be the individual weightage of each point. Yeah. Okay. That would be
Yeah,
zero if
no,
yeah.
that is not what it is. And also look
Yeah.
at this thing, right? I mean, it does make sense because
Yeah. Now it
you have
makes
now
sense. Yes.
you are asking me in the second case, you are asking me, even more even more concise thing that okay, not don't go
Yeah.
till 0.9, just 0.6. So it is
Yeah.
becoming, it is an even rarer event because it is a small range that you are looking at.
Okay. Okay. Yeah. Okay.
So
Yeah.
is
Got
that
it.
clear?
Thank you. Yeah. Super clear.
Yeah.
Yeah. Thank you. Yeah.
Yeah. So any other question? Someone else was also having a question, I remember. Okay. So if there are no, so
Okay. Yeah. Go ahead. Go ahead. Yeah. Hello. आवाज आ रहा? Hello.
to you because
Your
is
voice is lagging.
so
Piyush,
yeah,
your
here
voice
it
is
is.
lagging. Piyush.
Oh, my voice is lagging, is it? Is it still lagging right now?
No, no,
Hello?
no. Now it is okay. Now it is okay.
Okay, thanks. So there might be some, fluctuations here. I don't know how to deal with it. But, okay. So this is done. Okay. So let's talk about something else. Yeah. Now I think we should. Again, we are like. Okay, we are taking a lot of time in the basics. So is this fine, or should I, pace it up, or go faster,
Yeah,
something
this
like
is
that? What is
fine.
your
Yeah, you can
opinion?
go faster. If we have any queries, we'll ask you.
Okay, thanks. So now this is what we should, so the goal of the, learning all of these things was, this thing, what we were at start, this random variables. Okay. So now we can formally see what random variables are. Okay. Random variables. So if x is a, so x, okay, x, okay. So random variables, as I said earlier, it is not a variable that is random. It is formally, it is a function, function such that, let me write these things. So first, so let's say if x is your random variable, it is a function that maps your omega uh, to a real number r. Okay, and this is also, it is f measurable. Now, I won't cover what this f measurability means. Okay, this part is something that would, take up the, it is not something that we need to worry about right now, but just to make things complete, it is a real number. So it is a function, it is a set function that maps omega to r. Yeah, and it is a f measurable function. What f measurability means is something even deeper. I don't want to go into it, and because we are already, lagging behind. So just okay, take my word for it, and maybe look it up if you want to, if you are interested in there. Okay. So so okay so we will say, so you would ask me, okay, you are saying it is a function. Okay, well, let me give you some example to, satisfy, make you, to maybe convince you. So okay, so omega for a coin tossing example is x comma t, and let's say, you know so okay, the way I used to see is this omega f and p are this tuple creates what we call as a probability space. And this random variable x maps this to R, something called Borel sigma algebra that we discussed, and something called distribution function fx. But we will see what those things are. So let's say you are looking at the coin tossing example, which has two possible outcomes, heads and tails. Yeah, and so x, you want to define your random variable. Okay, so as I said, x is a function that maps elements of omega to a real number. Okay, so let me define what is x of, let's say, h. Now, h is an element of omega, right? So I want to say how does this random variable work? And it is up to me how I want to define, a random variable. So I say that, okay, x of h is, 1, and x of t is what? It is 0. So, whenever we, talk about heads and tails and things like that, we generally work with ones and zeros. So actually, your random variable is actually mapping this h comma t thing to 1 comma 0. This is what it is. So this is a random variable. It is a function. Remember that it is a function that maps the elements of omega to the real number, to a real number. Okay, and it is f measurable. F measurability is something that you can either look it up on your own, or it is not necessary for this thing. Okay, yeah. So I think we are done with random variables. Okay, so many theory to define a simple thing like this here. But you will see, if you go in some depth, I mean, this has very complications to it. Okay. Now, let me. What should I do? I think let us uh, let us talk about what. Should we talk about expectations now, or? Okay, let me talk about uh, something called distribution functions, perhaps. So let me talk about some general random variables. Okay, let me start with it. General random. So this is something that I think you have already studied in your undergrad. Okay, so let us start with something like, okay, so binary random Bernoulli. Okay, Bernoulli random variable. Okay, what is a Bernoulli random variable? So a Bernoulli random variable is basically a coin toss. Okay, so there are two possible outcomes. So your omega is actually something like 0 comma 1. Okay, and probability of x of omega equal to 0 is half, is, let's say, p, and probability of x of omega equal to 1 is 1 minus p. It's like heads and tails. Okay, you can see this as heads and this as tails, or other way around, whatever you prefer. So this is also a simple thing, right? It's a simple Bernoulli random variable. Another common random variable is what? Binomial random variable. Okay, binomial RV. What is the binomial RV random variable? So the binomial random variable is defined as the follows, right? Okay, it is the, so if I given n coin tosses, uh, the number of, what are the number of hits? Okay, what are the number of hits that you observe? So, for example, let's say that you have, so okay, let me write this as probability of x of omega instead of x of omega, I will just write x. Okay, x is your random variable. X is equal to k. So what does this mean? So given you have n tosses, okay, what is the probability that k of them are heads? Is what this is asking. Okay, so if you know some combinatorics, so what it requires means that there are n coin tosses. I need to choose k of them. Okay, and to these k of them I need to assign the I want these to be heads, right? So I want these to be heads, so I take p to the power k, so because the probability of heads is p, and I want the rest of them to be tails. So the 1 minus p of them should have a probability of, sorry, one of so the n minus k of them should have a probability 1 minus p. This is what it is. Okay, and k can go from what, 0, 1, 2 till n. You can have maximum n hits. This is what binomial random variable is. Okay. Similarly, there is another random variable which is quite famous, which is Poisson. Poisson, or some people don't call it poison. Okay, it's not poison. It's Poisson, or look at it's. I call it Poisson. It's not poison because it gives a wrong impression. Yeah. So what is Poisson random variable? So you can just now just remember the you can just remember the expression for the probability of this event. Okay, it is again a discrete random variable. The probability here with of x equal to k is lambda to the power k e raised to minus lambda upon k factorial. K can go from 0, 1 till here. So okay, I mean where lambda here is a quantity, is a fixed quantity. It's a parameter of this distribution. Okay, is a fixed parameter. So it can be 0.2, 0.1, or 0.5, anything you want. So this is another random variable. Okay. Another example of random variable is geometric random variable. Another famous one, geometric random variable. Here the probability of x equal to k is, so this probability you can think of as a, so what is the probability that you encounter the first head at kth coin toss? Okay, so okay, let me write it. Probability of uh, heads, so first head coming up at kth toss. And so if you think about it, you want the first k minus 1 to be tails, right? So this is 1 minus p is the probability of tail, and you want k minus 1, first k minus 1 of them to be this. Uh, oh wait, I think no, this is not what it is. Uh, uh, One head in k tosses is what this is. So if I toss a coin k times, I want only one of it to be
Hello, Piyush, your voice is lagging in between. Hello. Hello.
I think the net is there. Hello, am I audible?
Yes, now you are audible. Now you are audible.
Yeah, is this, am I audible clear? Is it a bit better now?
Yeah, it is better now. Yeah.
Okay, so I have changed the network. Maybe this would have, less effect on it. Okay. Okay. Uh, so I think this is correct. Probability of one head in k tosses. Okay. So you choose any. Uh, yeah. So I think this will be, k minus one of them should be tails. So that is probability. That is with probability one minus p, and one of them should be heads. That will be with probability p. Okay. So these are like general random variables that you people usually talk about. So you should just know them. So when someone comes and says, okay, do you know Bernoulli random variable? You should know that, okay, what it is, just a coin toss that he's talking about. And similarly for these other random variable. But yeah, it's not a must do thing. It's a good practice to remember them. That's all. Okay. So now let me, go to some, even, so these were all discrete random variables, right? So let me, take up some, continuous random variables, yeah. So like uniform random variable. Okay. So uniform random variable. Uh, what is the so yeah. So okay. I have So, okay, how do I do it now? Yeah. Okay, so if a random variable x, if x is coming from a uniform density, it is uh, it is defined. Uniform density is defined by parameters a and b. Okay, and there is something called distribution function. Okay, let me write this down first. So this is 1 over p minus a. You can think of this thing here, this quantity here, as some sort of weight that is assigned to a point x. Okay, so for example, how would this look like? So if this is your line, okay, so this a, this is b. Uniform density basically assigns a weight of, this is your real y-axis, this yeah, so okay, so this is assigns you a 1 over p minus a. Okay. So uniform density is something like, each element in this range is equally likely to occur, is what it is saying. Okay. So if it is equally likely, then the length of this is again b minus a. And since each of these points are equally likely, so it should be, the density should be 1 over b minus a. What density actually means is that, if I take some point here and I perturb it with, let's say, plus minus delta, roughly 1 over b minus a is what what is the amount of weight that is put here, is what it says. That's all. Yeah. Okay. I don't know if I was clear or not, but if you have any doubts, please let me know. Okay. Coming to exponential density, exponential random variable. So if in this case, if let me just write down the expression for the density functions here. So fx of x here for an exponential random variable is lambda e raised to minus lambda x, and the condition here is that x should be greater than 0. So if lambda is equal to 1, fx of x is what? E raised to minus x. How would this look like? This will just look like a simple exponential function, decaying exponential function. So this is 1, and this is like going downwards. This is what it is. Okay. So this is exponential random variable. Just remember, you need not even remember the expression for it, but it's a good habit to just know these things. And the last thing that I would like to for you to know is that a Gaussian random variable. This is perhaps the most important of all the random variables. You keep saying this again and again, and the expression for this is fx of x is 1 by sigma root 2 pi e raised to minus x minus mu whole square by 2 sigma square. So what this is telling you is, it's, let's say there is this point mu, and the exponential density looks something like this. Okay, so it is like a bell-shaped curve. Okay, and in some sense, the width, this width, okay, this width is what is characterized by sigma, the variance, so to say. So this the width of this bell curve is characterized by sigma, and the center of this curve is characterized by mu, which we call as the mean. Okay, so these are like the common continuous random variables that are useful to us, and we will keep using them. So any doubts till here? Please let me know.
No. Like, but can you give some a good example like you gave yesterday? Example
For
that can like sum up all of those things that you have taught until now. Like some,
can you? Yeah.
yeah. So like some sort of that brain teaser or something like that. Like,
Okay. Today I think there is not much. I mean, today's portion is like the routine thing. There is
okay.
not much of let me think about it. Can I come up with something? So probability. Can I have something? Uh, I think today's portion is not that much interesting. That's all. I think uh, yeah, I don't have anything today because it's mostly routine stuff that is there in probability. I think I suppose you already know these things.
Yeah,
Gaussian random
no worries.
variables.
Yeah, no worries, no worries. Yeah,
Sorry, what?
yeah, no worries. Okay, like so maybe we should move ahead.
Yeah, maybe it's like yeah. I mean, when we come to entropy and those things, perhaps then there I can do some interesting stuff, perhaps. Okay.
Okay, yeah, yeah.
Okay. So okay, now this was the end of most of the theory part. I mean, today's lecture is going to be boring, so then that is what it is going to be then, because it's some, yeah, as I told, it is a routine thing. Now coming to expectations. So this is again, expectation is something that gives you a sense of. I think you already know expectation, what expectation is. Do you guys know it, or I don't know? Are you aware of what expectation is? Hmm, I don't know. Is my voice broken again?
No, actually, I'm not sure. Your voice is okay.
Okay.
Yeah, we are actually not clear on expectation.
Okay. So okay. Should I go? Okay. So let me do it. Okay. Mm, okay. So basically, what is expectation? Expectation is actually what the English meaning of expectation is, so there is something that is happening and I have some expectations from it. Okay. What does it mean? It means that, okay, I think, something. So for example, let's say, sorry.
I'm sorry. I get you. You meant English expectations.
No, 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 no. I meant.
I thought you
Uh,
meant some mathematical expression or
Yeah, yeah,
something.
I do know. That is what I meant. So I am just explaining what is expectation. Okay. Yeah, I know that you know what English meaning of expectation is.
Yeah, just because you said, do you know that? I thought you meant.
No, 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 no. Yeah, it's fine. So what I was saying was, let's say there is a match going on, and there is some expectation. Okay, so people keep using this term, right? That okay, I expect India to make some runs around, like, let's say 300. This is my expectation. So what does it exactly mean? What does expectation exactly mean? So mathematically speaking, expectation is something that you if a random experiment is taking place, you you with some mathematical certainty, you want to say, okay, this is what I expect from this random experiment. What This is the outcome that I expect. Okay. So the way people have defined expectation is, you so this is how people have defined expectation. So if x is a discrete random variable, okay. So I mean, what do I mean by discrete random variable? X is something like x1, x2, things like that, till xn, something like this. And someone says me, okay, these are the set of all possible outcomes. What is the expectation? Meaning, on an average, what do I expect the outcome to be? Okay. So it's not so the way people have defined it is the following. So you sum over I, okay, probability of xi, probability of x equal to xi into xi is what it is. So it's like a weighted sum. So if, for example, if you have heads and tails, okay, and with probability of heads is equal to probability of tails, which is equal to half, you know and let's say the random variable that I use to define this is 1, this to define is 0. Okay. So and I take the so I calculate the expectation, so this is x. So I basically take the expectation of x. This comes out to be so I see first thing that 1 into 1 by 2, okay, plus 0, which is this one, into probability of 0, which is half. This is what it is, and this comes out to be half. So you can see, since it was a fair coin, okay, since it was a fair coin, okay, I am expecting that what since half of the times it is going to be 0 and half of the times it is going to be 1, I am saying that, okay, the value of x is roughly half. When it doesn't mean that x is going to take the value half, because x can only take the value 0 and 1. Okay. It is just a mathematical intuition that, okay, since both of them is half, I cannot say what is going to come, so I am saying half. you know that is what I want to what is meant by expectation in vaguely. Okay. This is a very vague explanation, because if I go in details, and it has something to do with Lebesgue integral and things like that, things will become very complicated, and again we will lose some time. But this is a good enough, you can think of this as some sort of mean, actually. So when people say talk about mean, this is what they are talking about. Expectation of a random variable is what people refer to as its mean. Okay. And for example, let's say if I change few things, okay, if I say that, okay, probability of heads is let's say uh, let's say 1 by 4, and probability of tails is uh, 3 by 4. Okay, now someone says, okay, now these are the probabilities, what is your expectation? So I will say that, okay, I will go to my formula. I will say that, okay, so 1 is happening with probability 1 by 4, okay, plus, uh, yeah, so and and so this and 0 is happening with probability 3 by 4, yeah. So now this comes out to be 1 by 4, yeah. So, well, what does this mean? Since there is some bias in the coin, so the coin in some sense prefers the tails. The outcome of tail is more probable than the that of heads. Okay, because of this reason, my expectation has shifted from half to 1 by 4. What does it mean? So now my expectation is becoming less. I am if I see these heads as winning, okay, my chance of winning was in some sense, I am expecting less now, because the coin is biased, and I am at I cannot leverage it. So in some sense I am at disadvantage, and that's why my expectation has decreased from half to 1 by 4. So I hope I am able to convey what the broad idea of expectation is. Now, for discrete random variables, this is the formula. Well, what happens if your random variable is, continuous? And for example, it is Gaussian or exponential. What happens then? Well, in that case, also the formula for expectation of x will the summation would change into integral. Okay, it becomes minus infinity to plus infinity x f x of x dx. So again, you can see, right, that this is just, so this was a weighted sum. This is a weighted integral. I am taking x, each of my possible outputs, and I am weighing them by, a probability or a weight function, which is my probability. And I am calculating this integral, and this is what my expectation becomes. So if I have to, again take some example, uh, okay, so which random variable we should take? So let us take the let us take the uniform random variable, for example. So okay, so let's say x is coming from a uniform distribution is a comma b, and fx of x is what? If you remember, this was the length, 1 upon length of the interval, which is 1 upon b minus a. Okay, so what is the expected value of x? If I plug these things into my formula, this is minus infinity to infinity. Okay, so x into 1 over b minus a dx. This is what it is, right? And if I, so now, since the range of x here is, between, x is always between a and b, the limits will change from minus infinity to infinity to a to b. Okay, this will become x into 1 over b minus a dx. This will become, we know the integral of x is what? It is x square by 2, right? So 1 upon b minus a is a constant. X square by 2 is the integral, and this will go from a to b, and this will become what? B minus, so this will become b square minus a square by 2 times b minus a, and this will become a b plus a into b minus a. So this is what? B minus a into b plus a by 2 times b minus a. This will cancel out, and this will become b plus a over 2. So this is the expected value of a uniform random variable. And if you look at it, what did the uniform random variable look like? So it looked like something like this. So this was a, this was your b, and this was your density function. This thing was 1 over b minus a. Okay, since the weight over the entire interval was equal, so this was all equal. I should expect something in the middle to be my expected value, and that is exactly what it is. So this middle point, okay, So this thing, what is this point? So this is till here it is a, okay. So this till here it is a, so a plus, and we are halfway from a to, we are at midpoint of this interval, right? So we are at midpoint of this interval, and the length of this interval is b minus a, right? So if I add a plus b, so b minus a by 2, this this will become what? This is a lot of, yeah. So if I do this, this will become a plus b by 2, and this is what we have here as well. So it's it is in some sense it is just giving us what we already expect from a uniform distribution. Since it is assigning same weight to each of these points, the middle point is what I should expect, right? uh, uh, I think it is getting very boring perhaps, I don't know. So I don't know, do you guys want me to end here, or can I go for just 2-3 minutes and then we can complete this expectation and all those things?
Yeah, you just complete the expectation part today if you can, like if we do not have anything else left.
Okay, yeah, so let me do that. So another thing is that, okay, so for Gaussian random variable, right? Gaussian. Okay, what will be the expected value of x? So this will be, integral x 1 by root 2 pi sigma square e raised to minus x minus mu whole square by 2 sigma square dx minus infinity to infinity. So I am just writing this down. It is a simple, integral and mathematics. I don't want to bore you with it, but this will come out to be mu. And that is why, people call this thing, mu as the mean. So the expected value is in some sense nothing but your mean. Okay, that is what it is. Okay, now let me talk about one more thing. Okay, what about expectations of a function of a random variable? Okay, so you know that x is a random variable. Okay, now someone comes and gives you a function g, and he says that okay, g of x is what I need, and I mean take my word for it, g of x is also a random variable. Okay, so if x is a random variable, any continuous function of it is also a random variable. And he says that okay, now I want expectation of this new random variable that I have created. So what would that be? Expectation of g of x, what would that be? So this is nothing but again, this you just use the same formula. Okay, the formula was this thing. You had x here earlier into fx of x here. Okay, dx. This is what we had earlier. Okay. Now instead of x, he has given you g of x, so you just change this. Okay, you just change this thing. Okay. So instead of seeing what is the expected, so instead of taking x weighted average of x, instead of taking the weighted average of x, you take the weighted average of g of x, the new function that you are given, and that will be the expectation of your new random variable g of x. Okay. Generally, people also denote that okay, we are talking about expectation with respect to x here. So because what can happen is, I can, so there can be few ambiguities. It's a good practice to write the distribution here below, because let's say you have some f of x comma y, there are two distributions here. So now what with respect to what do I take the expectation? So it is a good practice to either mention, either x, or maybe you want to take expectation with respect to both x comma y. So you use the joint distribution of x comma y to calculate the integral and things like that. Okay, I think, yeah, so I think it is. So for example, let me take one more thing. So okay, so let's say you want to calculate expected value of x square, okay, or for a uniform random variable. So what will it become? So it will be x square into fx of x dx. going from minus infinity to infinity. That's all. So this was like expectation, and in general, you know, if you take expectation of x raised to k, okay, x raised to k, this is called the kth moment of x. So expected value of x is first moment of x. You know, expect. So if I do this, if I make this x square, this will be the second moment of x. So these are like important stuff. Generally, people remember first and second moment. Uh, some there is there is something called variance. Okay, variance of x, which is nothing but the second moment, which is expected value of x square minus square of the first moment. So this is the first moment, you take the square of it. This is the variance of a random variable. Okay, these are just formulas. So you calculate this thing, you calculate this thing, you get your uh, variance. Our people also write this as second moment of x minus expected value of x whole square. So I mean, you can see that actually take this as a homework. Actually, these two things are one and the same. There is no difference between these two things. I think I have bored you enough for today. I think because today was I don't know, it was not much of a fun, I guess, today. Yeah. Okay. So yeah, I think I want to end it today here. Okay.
Yeah.
Tomorrow maybe we can start with information theory and perhaps MLE and all we will cover tomorrow. That
Okay.
would perhaps be a bit more interesting. Maybe today's was, I agree. Since yesterday, okay. So let me just first end this recording. Okay. Okay. Stop recording.
Also, if you can share some material